And welcome to part 3 from chapter 10 for general chemistry. We're going to be finishing up the chapter on ideal gases. And the last topic that we really need to cover is this idea of partial pressures. And so far, what we've been talking about is, let's say, single gas systems, right? We've been able to use the ideal gas law to calculate properties of a single gas. But often when we're doing a reaction or as a reaction proceeds, we're making a mixture of gases. And so we need to talk about those mixtures and how partial pressures are used to calculate some of these properties. Now, partial pressures, especially when you read through the book or you watch some videos, it seems very complex. And on the next slide, you're going to see there's some pretty complex looking equations. But here's the kicker, right? The total pressure of a mixture of gases is the sum of the partial pressures of the individual gases, right? So the total pressure, right, P total, is just equal to the sum of the individual pressures. Now the question is, can we calculate individual pressures? Well, sure, right? P equals nRT over V, right? Now the tricky part becomes whether we're talking about total pressure, right? If we're talking about total pressure, or if we're talking about the individual pressures. But in both cases, P is equal to nRT over V. We just have to pay close attention to what data is given and then make sure we're applying the correct values into our equation. Down at the bottom here in the cartoon graphic there, you can see just a visualization of this. If I take some nitrogen, right, and I take some oxygen and I mix them together into a flask, right, the pressures are additive, right? 190 plus 90 is equal to 280. So the individual pressures make up the total pressure of that flask that we have, okay? So let's do a little bit of math, right? This is the exact same idea that we just talked about, right? The total pressures equal to the individual pressures. We just swap, right, the ideal gas law in for the individual pressures here, and we draw out some of our constants, right? And if we do that, right, we can basically get to this idea of a mole fraction, right? A mole fraction, which is just the individual pressure, right? The individual pressure divided by the total pressure, right? Which is equivalent to the individual moles divided by the total moles. That is equal to a fraction. And if we add our individual fractions, we should add up to be 1. Therefore, what we can say is that the individual pressure, right, the individual pressure here, P1, is equal to some kind of fraction of the total pressure, right? Some kind of percentage. Again, this is no different than if I asked you to, let's say, calculate the weight percentage of your body that is your legs, right? Your legs make up a certain percentage of your total body weight, so the individual weight of the legs is equal to some percentage of your total body, all right? It might be a little bit of a weird analogy there, but it's the same idea here, okay? An individual pressure of a mixed gas system is equal to some fraction of a total gas, of a total pressure for a mixed gas system. All right, so hopefully I haven't lost you or scared you away yet. Let's start to work some examples and kind of see how this stuff falls out. Might clarify some things here. So a 500 ml flask, and it gives us some temperature and pressure, contains some neon and a value, right, half a gram of argon. And it asks, what is the mass of neon in the flask? Okay. So let's think here for just a second. What information are we given? Well, we're given volume is equal to 0.5 liters. Okay. That's this right here. We're given pressure. I'm going to convert 750 millimeters of mercury into atmospheres just because I have the constant for I have the ideal gas constant for atmospheres. You can use either one. It really doesn't matter. You don't have to do that conversion. We're given temperature, right? I'm going to go ahead and convert that into Kelvin, so 318 Kelvin, all right? And we're given one last bit of information that we always have, right? R, right? We always have R around. So 0.08206 liters, atmospheres, mole, Kelvin. Okay. All right. So let's talk about just for a second here what's going on. Well, we know our overall equation is equal to, right, PV equals nRT. Now we need to figure out mass of neon, right? Mass of neon is in some units of grams, right? Anywhere in our do we have anywhere in our equation here something that's in units of grams? Well, the answer is no, right? But we do have units of moles, right? N, right, is equal to moles. So if we could figure out moles of neon, right, we could swap that into grams of neon, right? We can do mole to gram conversions, or hopefully we can at this point. Okay, so that's what we need to do. We're going to rearrange this equation to solve for N, right? N equals PV over RT. Do we have a value of P? Yes, we do. Do we have a value of V? Yes, we do. Temperature and R, right? So we can solve for N. But here's where we need to pause. Take a look back at the question. What is it saying? We have a 500 milliliter flask that contains neon and argon, and it gives us the pressure, right? 750. This is the total pressure, right? It's the total, the mixture of the two. So what we can figure out is the total moles, right? N total, okay? Because we have information about the total pressure of this system. So let's work this out. So N total, the total number of moles, right? The total number of moles of the system is equal to 0.9868 atmospheres, right? That's the pressure from the total mixture that we have. 0.5 liters. So far, so good. R 0.08206 liters atmospheres, mole Kelvin, and temperature. Whoops. Sorry, I put my decimal in the wrong place there. Not 3.18, but 318.15 Kelvin. All right. And if I solve that out, I got N total is equal to 0.01891 moles. Okay. So the total amount of moles in my flask is 0.01891. Now, what is N total equal to? Well, N total is equal to N of argon plus N of neon, right? The total number of moles is equal to the moles of argon plus the moles of neon. Can I figure out moles of argon? You bet, because I've got grams of argon up here, right? If I can figure out moles of argon, and I know my N total, I can figure out moles of neon. And if I know moles of neon, I can convert moles of neon into grams of neon. Got it? So let me run through that one more time. We just figured out total number of moles. Total number of moles is equal to the moles of argon plus the moles of neon. We're given information about how much argon we have, so we can figure out moles of argon. And we just calculated the total number of moles. So we can figure out moles of neon. So that's what we're going to do next. All right, so let me see if I can keep this on the screen here. So we were given information that we have 0.05 grams of argon. We convert that into moles, 39.948 grams for every 1 mole of argon. 0.01252 moles of argon. My total number of moles, right, is equal to moles of argon plus moles of neon. If I rearrange this equation, moles of neon is then equal to, I got 0.00639 moles of neon. Okay? And then we finally take moles of neon into grams of neon. So for every 1 mole of neon, we have 20.179 grams of neon. 0.253 grams. All right, let me zoom out so we can catch all this together here. I'm going to erase some of this stuff to clear it up so you guys can hopefully see what our progression was here, okay? The trick, well, not really the trick, or the thing to pay attention to is that this information is given to us for total pressure, right? For the mixture together. So we have to separate out the individual components. All right, next problem. A valve opens to mix and react some nitrogen monoxide, and it gives us some values, and oxygen, right? In the following reaction, right? And it asks us to determine the composition, the mole fractions of the mixture, and the partial and total pressures of the system. Okay, right, so this is a pretty complex, this is a pretty complex problem. Now, we're doing a reaction, right? We're doing a reaction and we're given information about both of the starting materials. Now, to be honest, right, giving us information in about volume and atmospheres for both of these isn't too useful, right? We know we're doing a reaction. Now, we're very used to dealing with reactions in moles. So what's the first thing that I'm going to do is convert everything into moles, right? You say, well, how did I know to do that? Well, it tells us to calculate the mole fraction, right? So let's go through and do this, right? We're going to convert this information and this information into moles of those gases respectively, okay? So moles of NO, right, is equal to PV over RT, right? I just rearranged my ideal gas law. So I plug in this information. I have 1 atmosphere. I have a volume of 4 liters, 0.08206 liters atmospheres, mole Kelvin. And my temperature is 25 Celsius, right? So 298.15 K. So I am given 0.164 moles of nitrogen monoxide. Okay. Moles of O2, right, is equal to PV over RT. Pressure was 0.4 atmospheres. 2.0 liters. The constant is the same. Temperature is the same. And I get 0.0327 moles of oxygen. Okay, wonderful. Now we have a little bit more information here, right? Now we're something that we're a little bit more comfortable with. Now we could even read the question and say, you know, we mix 0.164 moles of nitrogen monoxide with 0.0327 moles of oxygen, right? How much NO2 gets made, right? Or how much of everything is left over. Uh-oh, right? Do you guys see what the problem is here? This is a limiting reagent problem. We have to know what our limiting reagent is. So do you remember how to do that? Well, remember, to get our limiting reagent, we need to compare, right? We need to compare how much product gets made. Actually, let me do that in red. We need to compare how much of our product gets made from each of our starting materials. So we need to do some stoichiometry here. Now we can do this one in our head, right? Just because I want to keep this recording a little bit short, I'm going to skip and tell you that our limiting reagent is our oxygen, okay? There are past videos that I have that tell you how to get limiting reagent. It's not any different in this case, okay? Don't get tricked just because we've got a gas suddenly here that something's different. It's not. Our limiting reagent is going to be our O2. So what does this tell us? Right? What does this tell us? Well, remember, our limiting reagent is what gets used up completely, right? It gets used up completely. That means after we mix these things together, the oxygen is completely gone, right? It's completely used up. But does that mean that my NO is completely used up? Well, the answer is no. We still have some NO left over. So in our final mix, let me change colors here. In our final mixture of our gases, right, is going to be everything that's left over. It's going to be a mixture of NO plus NO2. The O2 is used up to make our NO2, and the NO was our excess reagent. So our final pressure, right? Our final pressure is going to be a mixture of NO plus NO2. So we're going to have to figure out the pressures of both of those systems. All right. So how are we going to do this? Well, the easiest thing to do is to kind of set up a table. So let's do this. What I do is I'm going to write my reaction again, right? Okay, this is my reaction that we have from up there. I'm going to make what's called an ICE table, where ICE just stands for initial, change, and we'll say ending for now. Okay, the initial amounts that we have, what happens what happens during the reaction for changes, and what happens at the end. So my initial is the stuff that I calculated up here, right? 0.164 moles. I initially have 0.164 moles of that. I initially have 0.0327 moles of this. And I initially have none over here, right? We don't start out with any of our product. What happens as my reaction proceeds? As my reaction proceeds, I use up all of my O2, right? I consume all of my O2 because it's the limiting reagent. So I lose that many moles. Well, if I lose that many moles, right, I have to use up NO, right? I have to use NO to do that, to do this reaction, and I consume that many moles of NO, right? How did I get that number? Stoichiometry, right? A 1 to 2 ratio. A 1 to 2 ratio. Okay. I consume all my oxygen, I consume some of my nitrogen monoxide, and I make some nitrogen dioxide. So what happens at the end? At the end, I have 0.099 moles of NO left over, and I have 0.0654 moles of NO2. So what does this tell us? Well, this is how many moles we have, right? And total is equal to moles of NO plus moles of NO2. So I'm going to just plug those values in. So N total is equal to 0.164 moles. Now, what is this going to tell us? Well, let's scroll back up, right? What are we trying to figure out? The mole fractions, right? So we're trying to figure out the percentage, so to speak, right? We took care of the composition, right? The composition is what we just finished doing, right? The composition is that many moles of NO, right? And that many moles of NO2. Now we need to figure out the mole fractions. So we have our total. So our mole fraction, right? Our mole fraction for NO is equal to the moles of NO, 0.099, over the total, and the mole fraction for NO2 is equal to 0.0654 moles over 0.164 moles. And if we just plug that in, this is equal to 0.6, and this is equal to 0.4. So 60% of this and 40% of the moles is roughly what we're talking about here. Now pause this video, go back and follow through with the math here, right? See if you guys can see what we were up to, right? We took our initial data and turned it into moles. We made these ice tables to see what happened as we went through the reaction. We got our total number of moles, and then we figured out our mole fractions. Now, let's look at the second part that we need to take care of. We need to figure out the partial and total pressures of our system. Okay? The partial and the total pressures of our system. Let's gather some information together, right? We know our total number of moles. It was 0.164, right? Our final volume is equal to 6 liters, right? Because this question told us that we mixed a 4-liter and a 6-liter container together, right? We mixed a 4 and a 6-liter, a 4 and a 2-liter container together. Our temperature, we have to assume, didn't change. Otherwise they would have had to tell us. And R never changes because it's a constant. So what are we going to figure out here? Well, we're going to calculate our total pressure, right? Because we're dealing with total moles here. So P total is equal to nRT over V. So P total equal to 0.164 moles, 0.08206 liters, atmospheres, mole Kelvin. 298.15 K divided by volume. So P total equal to 0.669 atmospheres. Now we need to figure out the pressure, the pressure of NO and the pressure of NO2. Well, remember the partial pressure of NO is equal to the mole fraction of NO times the total. And the partial pressure of NO2 is equal to, whoops, I meant to do that in red. The partial pressure is equal to the mole fraction of NO2 times P total. And hey, look up at the top, right? We've got our partial pressures right there. So the partial pressure of NO is equal to 0.6 times 0.669 atmospheres. And the partial pressure of NO2 is equal to 0.4 times 0.669 atmospheres. And I've got 0.27 atmospheres. And over here I got about 0.4 atmospheres. Now, even I will admit, this was a tricky problem set, right? This was a tricky problem. What is the big tricky part of this, though? Well, you've got to go and you've got to think about what information is being given, right? And you break it down a piece at a time. One very practical example of this partial pressure is when we collect a gas over water. Now, water has a vapor pressure, right? Water has a vapor pressure. And we can actually measure, and there is a table of data, right? There is a table of data where we can actually pull information about the partial pressure of water at certain temperatures. And so often in the book, you're asked to calculate the pressure of a system when it's collected over water. And so we're going to have to use this table of data, and I've just copied part of it into here so we can use it. But let's see how a question like this is asked. So a sample of potassium chlorate was heated and 465 milliliters of oxygen was collected over water, right? What mass of oxygen was collected? And they give us a temperature and they give us a pressure, right? Now, if you look on the previous slide here, right, the total pressure is equal to the partial pressure of water, right, plus the partial pressure of whatever gas it is. So the total pressure, P total, is equal to the pressure of O2 plus the pressure of H2O. Now, we already know what the pressure of H2O is. It's equal to 21.1 torr. How do I know that? Well, it tells me right there, right? 23 degrees Celsius, it gives us the value for that. So now we have to ask, well, what is this number here? Well, that value there is my total. P total is equal to 750 millimeters of mercury. And P total is equal to the sum of the two partial pressures. So we're going to do a magic conversion here, right, and be able to figure out the pressure of O2. Now, it just so happens that torr in millimeters of mercury, for every 1 torr, you have 1 millimeter of mercury. So this makes our math a little bit simpler, right? So PO2, right, the partial pressure of O2 is equal to P total minus P H2O, right? So the pressure of O2 is equal to, I got 728.9 torr, or millimeters of mercury, whichever one you want to use. Got it. So again, total pressure versus the individual pressures. Now what other information are we given? Well, we've got pressure of O2. We've got volume, right? Volume equals 0.465 liters, right? We have R. R is equal to our constant, right? 62.36 liters, right? Liters torr mole Kelvin. And we are given temperature, 23, right? Temperature is equal to 23 Celsius, which is equal to 296.15 K. Good. Now we can solve for N, not N total, pardon me, number of moles of oxygen, and that's equal to our pressure, 728.9 torr, times our volume, 0.465 liters, constant 62.36, temperature. And plugging that into my calculator, I got that equal to 0.01836 moles of O2. And we're almost done. Moles of O2, for every 1 mole of O2, 32 grams of O2, which is equal to 0.588 grams of O2. Mass, right? What mass? So again, pause and take a look at how we walked through this, right? Anytime you see the statement in your question that we collected it over water, we have to realize that we have to factor water, the pressure of water, into our equation. And the last topic that we want to talk about in this chapter is just reality, right? In reality, not everything is an ideal gas, right? But it really depends on pressure and it depends on temperature. And so the van der Waals equation has some corrective values in there to kind of account for high pressure or low temperature systems. But if you take a look at the van der Waals equation down there at the bottom, you see it's actually very similar to what we see with our ideal gas law, right? We have P and V, right? A derivative of P and V is equal to nRT, right? With some corrective values in there. Now, we're not going to do anything with this equation for this course. It's just, it is talked about in the book, and we do have to point out that reality is a little bit different from what we talk about in here. That being said, that's the end of chapter 10. And if you have any questions, please swing by my office. Don't forget to work the problems in the chapter and at the back of the book also.